Hello dear students. So I'm going to cover some topics which troubles the student, which I've seen that many of the JEE aspirant, whether it's JEE main or whether it's JEE advanced aspirant, they struggle with those topics. So I'm going to cover those topics in my theory sessions. So today we are going to cover the topic of radiation pressure from modern physics. I've seen students struggling around this topic. If the questions are easy, they are able to do, but if the questions become tough, then generally the students are not able to do. So we are going to cover this topic today, and let's get started right away. So I'll write the name of the topic, that is radiation pressure. Okay, so this is the topic that we are going to cover. Okay, now guys, there are two popular situations that are given when we are when we are asked to find out the force due to radiation, and the two situations are we might be given a parallel beam. Okay, we might be given a parallel beam, and we might be given a point source or a tiny source, a spherical source from which the rays emerge out in all direction. Okay, so these two are the generally the given situations. Okay, and when I'm taking this session, students, I'm assuming that you already have a background of photons. Okay, like this is not a session that I intend to teach you from zero. I'm assuming that you are familiar with properties of photon, you are familiar with how to write the energy of a photon, how to write the momentum of a photon. So if you are aware of these, so if you are aware of the basics of the photons, then this session is for you. Okay, so these are the two situations. The first situation, let's start dealing with it. So the first situation is the situation in which we are given a parallel beam. Okay, so the situation is like this. Let's say we have a plate. Okay, we have a plate like this. Okay, the dimensions are given to us. Let's say this length is A, let's say this length is B. Okay, so that the plate area is AB, and we are also given the reflection coefficient. Okay, we are also given the reflection coefficient of this plate. It tells us what fraction of energy will be reflected back by this plate. If the reflection coefficient is 0, then we are talking about a black body, something that absorbs all the energy incident on it. And if the reflection coefficient is 1, then it means that we are talking about a perfect reflector. It will reflect all the energy that is incident on this. So till now I haven't drawn the beam. All right, so this is my object, and I intend to make incident on this beam, on this plate, a parallel beam of light. Okay, we intend to make incident a parallel beam of light. Okay, the intensity of this beam would be given to us. So intensity is watt per meter square, and for now let us assume that this beam is monochromatic. Okay, for now let us assume that this beam is monochromatic. It has only one wavelength lambda. Later on we will see whether we require to impose this condition or not. We'll see that later on. Also, if I draw a normal to any point of incidence on this plate, okay, then this angle would be called as the angle of incidence. So let us assume that we are also given the angle of incidence. All right, so let me just summarize what are the given quantities. We are given the intensity, we are given the wavelength, we are given the area of the plate, we have been given the reflection coefficient, and yeah, we have been given the angle of incidence. So these are the quantities that are given to us. And what is our aim here? Our aim is to figure out how much force will this plate experience because of this beam. All right, that is our intention. Now guys, what I will do, I will first mention the expression of the force. Okay, so that students who are only interested in knowing the expression can know the expression and they can proceed on. Okay, but here I will first mention the expression, then I will derive the expression. The students who are not interested in deriving the expression may omit that part of the video. They can move forward in the video and they can continue from after the derivation. Okay, so let me first mention the result. Okay, so if we are looking at the figure, such that only one edge of the plate is visible to us. Which edge? I'm talking about this edge. So we must be viewing from somewhere around this. So this is, let's say if this is the eye of the observer. Okay, then the observer will view only this edge of the plate. Let me name it as A, B. Okay, let's call this as C. So in this figure, only AB edge would be visible to the observer, and the light that is striking the plate will appear to be coming like this. Okay, the light which is striking the plate would be appear to come like this, and the angle of incidence would be this. So in this case, students, if I ask you to estimate that what will be the direction of force in which what will be the direction of force that this plate will experience, you will probably tell me that the direction would be like this, like one of the components will be parallel to the surface and the other components would be perpendicular to the surface. So let me write it as F parallel, let me write it as F perpendicular. If you thought like this, if you predicted this, then you were correct. That is the how the forces will act. And what is the formula, guys? So the formula for perpendicular component of force would be IA cos square theta 1 plus r divided by c. Here c is the speed of light. Okay, and F parallel would be IA cos theta sin theta into 1 minus r divided by c. So notice that we have written both the expression in terms of the parameters that were assumed to be given. So this is the formula. Those of you who want to omit the derivation, you can learn this formula and then you can continue this video from where I start taking the examples. Okay, those of you who are interested in the derivation, here we go. So our next job is to derive the expression that I just did. Now, let me also tell you who should be interested in knowing the derivation. So guys, there will be questions that will require you to do those steps that we are doing in this derivation. Okay, there will be questions, and such questions you can expect only in JEE Advanced examination. They will not be there in JEE Main examination because they would be too lengthy and they would be too insightful for a JEE Main pattern paper. Okay, so this derivation should be done by students who are very sure that they are preparing for JEE Advanced examination. Those of you who have absolute clarity that you are only focusing on JEE Main, you can omit the derivation. Okay, now let's continue. So I'll draw this view only because this view is the easiest one to understand what is going on. Okay, so let me again draw the same view. So this is the plate, trying to save space by drawing a smaller figure. Okay, and now pay attention that how light is incident. So I will draw the true extreme rays that are incident. Okay, so if I want to talk about that, how much power is incident on this plate? Okay, will you agree with me that from this point, if I drop a perpendicular to this beam, then whatever power, whatever energy is coming within this region, that is the energy that is ultimately going to be incident on the plate. Because if you agree with that, then we can actually make a general rule around this, that see, if this angle is theta, which is the angle of incidence, then this angle will also be theta, and this length, let's see what we named this length. We'll name this length as A. Okay, so this length will be A. Okay, this length is A, which means that this length will be A cos theta. All right, which means that the area from which this plate is receiving energy would be written as A cos theta into the depth of the plate, which is B. Okay, or in other words, A cos theta, this is the area from where the plate is receiving energy. So if I have to talk about the power incident, if I have to talk about the power which is incident on the plate, okay, it would be I multiplied by this area, intensity multiplied by this area, which is IA cos theta. And what you can do, you can actually remember this as a standard result, that if there is a parallel beam of intensity I, which is incident at a plane area A, at an angle of incidence theta, then the energy incident on the plate is given by IA cos theta. You can remember it as a standard formula because you will require it in many questions. Okay, so that is one thing. Now, if this is the energy incident, okay, let me also number the equations, because later on, if I have to refer to an equation, I'll refer to that equation by the number. Okay, so let's call this as equation number 1. Okay. Now this is the incident power. If I talk about energy of one photon, okay, energy of one photon, how much energy is there in one photon? So that is hc by lambda. Again, this is something that you already know as property of the photon. So let me call this as equation number 2. Now if I write small n I, okay, this I want to represent this as the number of photons incident per second on the plate. Incident per second, or you can say per unit time. Okay, number of photons incident per unit time on plate. So how do I write this? So guys, understand this. If these many photons are incident in 1 second, okay, and this is the energy of one photon, then the product of these two will give me the total energy incident in 1 second. In other words, it will give me the power incident, because power incident is what? It is energy incident per second. So these many photons are striking the plate every second. Each photon has this much amount of energy. The product of these two give me the incident power. So if I multiply these two, I should be getting this. From here, I can talk about Ni. Okay, so let me do that. So Ni will be given as the incident power divided by energy of one photon. Okay, so this will give me the number of photons incident in 1 second. So that will be Ia cos theta divided by energy of one photon was hc by lambda. So hc by lambda. So this becomes Ia cos theta into lambda by hc, and let me call this as my equation number 3. I hope 1 and 2 were written. So this is my equation number 3. So this is Ni. This is number of photons incident on the plate in 1 second. Okay, now that's the number of photons. Well, very well. Now let's come back to this figure and let me talk about any one photon. So one photon is coming like this and it is striking the plate at an angle theta. Okay, let me choose x-axis like this and y-axis like this. So the photon is coming at an angle theta with the y-axis. Okay, I have chosen x and y-axis. My intention is to write the momentum of one photon. So let's do that. Okay, let me write it here again. This is x-axis. This is the chosen y-axis. The photon is coming like this along this line, which makes an angle theta. So this is the direction along which the photon is coming. Okay, so you know that how to write a vector. So I'm going to write small p. Small p indicates momentum of one photon, p1i. So what do I intend by this? I intend to write momentum vector, actually momentum vector of one incident photon. So how do I write it now? I will write it as the magnitude of the vector, which is h by lambda, multiplied by the unit vector in the direction of the vector. So a unit vector in this direction would be cos theta j cap sin theta I cap. So let me write it as sin theta I cap plus cos theta j cap. So this is the momentum of one photon that was incident on the plate. Let me call this as equation number 4. Okay, now see this. These many photons are striking the plate in 1 second and one photon has this much momentum. So the product of these two will give me the incident momentum per second. How much momentum was incident on the plate per second? That will be given by the product of these two. So let's do that. Okay, let's do that. Next, I am writing capital P. Okay, now or let me continue with small p for momentum. So I am writing pi. Okay, so what is pi? Okay, here we wrote p1i, so that was momentum of one photon. Now I am writing simply pi. This is total momentum incident on plate in 1 second. I'm not writing on plate, incident in 1 second. So this is the total momentum incident in 1 second. And how will I write this? Ni, this would be Ni multiplied by P1i vector. Okay. Okay, so let's do this. If I multiply these two, let's do this orally. H by lambda gets cancelled with h lambda by h, and then the vector remains. So Ia cos theta by c. Let me write it. It would be Ia cos theta by c, and then we will have this vector sin theta I cap plus cos theta j cap. Okay, sin theta I cap plus cos theta j cap. Okay, so this is the incident momentum in 1 second. Let me call this as equation number 5. Okay, so this is our equation number 5. Okay, well, so we have calculated how much momentum was incident on the plate in 1 second. Next, let's talk about NR. Now, what is NR? What was NI? NI was total number of photons incident in 1 second. So NR would be total number of photons reflected in 1 second. Okay, so this is number of photons reflected per second. Okay, or per unit time. Now, how do I write this? Okay, to write this, we are going to make use of the reflection coefficient. So, all right, we know that reflection coefficient is reflected energy by incident energy. So I should be able to write it as NR into energy of one reflected photon. Okay, I used symbol E1 photon. Okay, so and divided by Ni into Ei. Now Er and Ei are equal because upon reflection the frequency of the photon remains same. So this is going to get cancelled. Okay, so therefore we can write Nr, the number of photons reflected per second, as R into Ni. So this becomes R, and what was the value of Ni? Ni can be picked from equation number 3. It was Ia cos theta lambda by Hc. All right, so that would have become our equation number 6. This is our equation number 6 now. Okay, so we have written the value of number of photons reflected per second. All right, now my intention would be to write P1R. Now what it is? It is momentum of one reflected photon. It is momentum of one reflected photon. Now how do I write this? Okay, how do I write this? Again, we assumed x axis to be like this, y axis to be like this, and if a photon came at an angle theta, then it will be reflected at an angle theta like this. The ones that are going to be reflected will be reflected like this. Okay, so I have to, the momentum, the magnitude of momentum would be h by lambda. Okay, so I will write this vector. How will I write this vector? I will write it as, I hope it is visible. Okay, I will write it as h by lambda into, pay careful attention, sine theta I cap minus cos theta j cap. Keep in mind that we have assumed y direction downwards. Okay, so this is momentum of one reflected photon. Let me call this as equation number 7. And I know how many photons are reflected in every second. I know this is the momentum of one reflected photon. If I multiply these two, I get the total reflected momentum in 1 second. Okay, so let's do that. I'm going to write PR. It indicates what was PI? Total momentum incident in 1 second. So this would be total momentum reflected in 1 second. Okay, so that would be NR multiplied by P1R. Okay, so again, if I multiply these two, what do I get? H by lambda gets cancelled. I get IA cos theta R by C. Okay, IA cos theta R by C, and then sine theta I cap minus cos theta j cap. All right, now you would be wondering that what a great length of the derivation, but actually guys, once you understand what I'm doing, once I think it may have clicked to some of you that what I'm trying to do, but once it clicks, you will find that these things were pretty obvious, that this is what we should have been doing. Now let me number this equation. This is our equation number 8. Okay, so let's see where we are right now. Let's see what we have achieved till now. We have been able to write the momentum reflected per second. We have been able to write the momentum incident per second. So in 1 second, photons came with some momentum, and then their momentum changed. Okay, so what is that? Like, momentum change per second is what? It's the force, Newton's second law. The rate of change of momentum is equals to the force. So if I calculate the difference of these two, like see, this is the final momentum of the photons, this is the initial momentum of the photons. in 1 second. So change, like if I do let me do it here. If I do PR vector minus PI vector divided by 1 second, because this change took place in 1 second, so that will give me force on photons. Force on photons, because this is the momentum change of photon. So if you're writing momentum change of photon, if you're writing rate of change of momentum of the photons, you will get the force on the photon. So this is force on photons. And who has exerted this force? Well, the plate was responsible. All right, the plate was responsible for changing the momentum of the photons. If there had been no plate, momentum wouldn't have changed. Okay, so this is force on photons by plate. But wait a minute. We were trying to find out force on the plate, not on the photons. So what we are trying to find out is force on plate by photons. What do I do now? What do I do? Okay, we obtained force on photons by plate, but we were looking to find out force on plate by the photons. Newton's third law says that these are exactly opposite of each other. Like these are action and reaction pair. So this should be negative of this, like this should be negative of this. So I should be writing PI vector minus PR vector by, actually 1 second, whether you write it or not doesn't matter. Okay, so when you finish this calculation, you will end up with the result that I told you before I started with the derivation. Let's finish this. Okay, let's finish this. So the force that we were looking for, force on plate, okay, force on plate by photon, I'm not writing it. So that would be PI minus PR. Okay, let me write it. What was the value of PI? PI was here. Okay, I try to write it by memory. So IA cos theta by C, and then sine theta I cap plus cos theta J cap. I think that was PI. Okay, and what was PR? That was IA cos theta into R by C, and then I think it was sine theta I cap minus cos theta J cap. We will just confirm it. Yeah, okay. All right, that's it, guys. That's it. Now you can collect the coefficient of I cap. So that would be how much? If I try to collect the coefficient of I cap, I can see that it would be IA cos theta sine theta. Okay, and then 1 minus R by C. All right, and if I try to collect the coefficient of J cap, it would be IA cos square theta. Okay, IA cos square theta into 1 plus R by C. Okay, and that's it. This entire thing, okay, this entire thing is your, this is your F parallel, and this entire thing is your F perpendicular, because J cap was perpendicular to the plate and this was parallel. So we have derived the results now. All right, so that was the derivation. I told this result to you here. Let me go back, and yeah, here was the result that I told you, and we have derived the same now. Now we are in a position to use it. Okay, so I hope we are good till this point, everyone. Okay, so let's continue. Okay, to familiarize ourselves with the result, okay, let's consider some special cases that will give you a bit of clarity. All right, I want to put things in a manner which comes intuitively to you, and to do that, let's consider the special cases. So let's consider the first special case. That would be a case of normal incidence. Okay, case of normal incidence, and let's make it a bit more special by adding one more condition: case of normal incidence on a perfect reflector. Okay, case of normal incidence on a perfect reflector. So this, whatever I've written in English, it translates into this mathematics: theta is 0 and R is 1. Notice that this entire thing is this mathematically. So in this case, if I check the value of the force F parallel, okay, this will become 0 on multiple accounts. In the expression of F parallel, sine theta is there, theta is 0. Also R is 1, so 1 minus R will also become 0. So F parallel is 0, and F perpendicular that you get, let me come back here. F perpendicular that you get, that becomes 2ia by c. It becomes 2ia by c. And if I draw the figure, what is happening? So this is a plate, and the photons are incident like this. All right, and they are incident like this, and after reflection they are going like this. All the photons are going like this. So we do witness that there is no change in the x direction, like there is no momentum change in this direction. And if I want to compare it with a situation of mechanics, okay, the analogous situation that you see in mechanics would be a plank, a stationary plank on which there is a ball which comes with some velocity v0 and then which bounces off with the same velocity, like elastic collision. Okay, the elastic collision situation. A plank is stationary, or a ball bouncing off a surface after suffering elastic collision. Okay, that would be the mechanical equivalent of this situation, to give you a hint what is going on here. Okay, in this situation, if I make certain changes, for example, if I say that, okay, let's keep normal incidence only. Okay, let's keep normal incidence only, and we are not restricting the reflecting nature of the surface to a perfect reflector. Like from this case, I am removing this condition. Okay, so now we are only talking about this case when theta is 0. So even in this case, as you can notice by putting in the formula, F parallel will still be 0, but F perpendicular will now be written as IA1 plus R by C. So what would be the equivalent? What is the equivalent situation in mechanics? Now the ball is striking with a velocity v0, but when it is bouncing back, it is bouncing back with a velocity which is less than v0. So now the collision is not perfectly elastic. It is somewhere between perfectly inelastic and perfectly elastic. All right. And what would be the case if I want to make this collision as perfectly inelastic collision? Then I have to make R as 0. The reflection coefficient will become 0. So I hope you get this point. So if R is 0, we are talking about the ball coming to this plank and striking it and sticking to it. Okay, if R is 1, then it is bouncing off with the same kinetic energy with which it came. And if R is somewhere between 0 and 1, then we are talking about a case of partially elastic collisions. Okay, now that was one thing. Now a third case we can consider where we can relax the normal incidence condition. So I'm talking about general incidence now. Okay, general incidence. So I'm not restricting theta. General incidence on a perfect reflector. Let's see what happens if the reflector is perfect. Okay, so again, what is the mathematical implication of this condition? So the mathematical implication is that I am saying that R will be 1. All right, other things are general, R will be 1. So in this case, if you again check the formula, F parallel is still 0. F parallel is still 0, and F perpendicular will become 2ia cos square theta by C. Okay, and what is the equivalent situation in mechanics? So this is a plank, and this plank is perfectly smooth, so it cannot offer any impulse in the horizontal direction. It cannot offer any impulse. So when a ball comes, let's say with a velocity v0, okay, it strikes at some angle and then it bounces off at the same angle with the same speed, because there was no friction impulse. There was no impulse of the friction, so it bounced off like this, and therefore there was no momentum change in the horizontal direction, and therefore there was no F parallel. All right, so this would be the mechanical equivalent of the situation. Okay, and finally let's come to a very interesting case. I would say the most interesting case, and that would be the case of a black body. Okay, so case of a black body, or you can say a perfect absorber. So in this case, we are saying that we will keep R as 0. Okay, so what happens in this case? Let's check out. It's a very interesting case, guys. It's a very interesting case. So I want you all to pay careful attention to what I'm telling. So let's say this is the plate. Okay, this is the plate, and light is coming at an angle. Let's say from here light is coming. This angle is theta. Okay, this angle is theta. Everything else is same, like the symbols I'm keeping the same. Now let's say there was a force in this direction which was F parallel, because this time F parallel will be non-zero, and let's say this was F perpendicular. so that the resultant force is somewhere like this. Okay, resultant force is somewhere like this. So this is the resultant force. Let this angle be phi. Okay, let this angle be phi. So how will I write F parallel? Okay, how will I write F parallel? That would be IA cos theta sin theta. Okay, so that would be IA cos theta sin theta. 1 minus R will only become 1 upon C. What about F perpendicular? That will be IA cos square theta by C. So when you put R equal to 0, these are the formula that you're going to get. Now pay attention. If I want to know the net force that is acting on this plate, I will have to, find the resultant of these two, square of this plus the square of this plus root of this entire thing. So that will give me F. Let's do that in a short while. And how about tan phi? How am I going to find phi? So tan phi will be given by F parallel divided by F perpendicular. Let's do this on the next page. So first of all, let's investigate the value of tan phi. That would be F parallel upon F perpendicular. And if you do that, I want you guys to do this yourself. F parallel upon F perpendicular. Note that it turns out to be tan theta only, which is actually surprising. It's phi equal to theta. So the direction from which the radiation was coming, all right, the force is exactly in the same direction. I deliberately drew phi significantly different from theta, so that you don't assume this, because there was nothing to assume. We discovered that actually phi is coming to be equal to theta. Not only that, let's also check the value of F, and you would be surprised. It is going to be F parallel square plus F perpendicular square and root of this. And when you do this, I want you to do this on your own, students. Do this and discover that it only gets IA, it changes to IA cos theta by C. And what is IA cos theta by C? It is the incident power on the plate. All right, or I can say that this is the incident power. Okay, incident power upon C. So that's it. Okay, very interesting result, very important result. And once we have got this result, we can actually argue in favor of this result. We can understand that why at all this result is coming. Okay, let's try to see that. What is happening with the black body? What is happening? Okay, a black body is absorbing everything that is incident on it. It is absorbing everything that is incident on it. So there is no reflected momentum. All right, in our derivation, the final momentum was the reflected momentum. There is no reflected momentum. So the final momentum is 0. All right, the final momentum is 0. Now pay attention to this. If you're trying to calculate, delta of any vector, if you're trying to calculate delta of any vector and the final value is 0, okay, then you will end up with initial value. And in fact, when we were trying to find out the force on plate, we took a negative of this. All right, yeah, this was the force. This would, like, when I'm trying to calculate the change in momentum of the photon, 0 momentum, because 0 is the final value, minus initial momentum. And if I do the negative of that, as we did in the derivation, we learned that the change is only the incident momentum. Like, change will become the incident momentum because there is no final momentum. So it's actually, now it seems logical that there was momentum coming from this direction and all of that is gone now. There is no final momentum. So what is the change in momentum? So this value, right, magnitude wise, this will be the value. Direction wise also, this will be the direction. So we now know that the force, like, if I draw it here, what is that I want you to conclude? That if this is a plate, okay, if this is a plate and if the radiation was incident in this direction, then the force will just be in the same direction, okay, in the direction of the radiation, and this force would be P intercepted. All right, P intercepted, whatever power this object has intercepted by C. This is the case of black bodies. All right, and pay attention that whatever logic I'm giving you right now, that will actually apply even if the surface is not a plane surface. So this is a very important result. It's a very important result. Let me give you some examples of this. What I'm trying to say is this. Okay, those of you who were not able to follow what I said right now, look at the examples. From the examples, it will become evident. If not, go back in the video, play it at a reduced speed. Okay, what I'm trying to say is this. There is a beam coming. Okay, the intensity is I. Okay, the intensity is I, and there is a sphere here. And this sphere is a black body. It's a black body. Now I want to know that how much force will be acting on this sphere and in what direction. The radiuses are in what direction. So I will ask you to check how much power is intercepted by the sphere, how much power it has blocked. So notice that if we were to think about a shadow that will be formed on, let's say, any imaginary wall that is behind, then will you say that the shadow will have the shape of a disk, will you say that the shadow will be in the shape of a disk? And can we say that whatever energy was supposed to be hitting the screen in this region, that energy has been blocked by the sphere? And how much that energy would be? This area would be pi r square. Okay, so the force acting on the sphere, it would be I into pi r square by c, because the energy that was supposed to be present in this region of area pi r square, that has been blocked by the sphere. So the force would be I into pi r square, and the direction of force would be the same as the direction of the radiation. Okay, I hope this part is clear to you. If not, let me give you more examples. The more examples you see, the clearer it will become for you. So let me go with this. Let me go with the next example. So 1, 2, 3, 4, 5, 6. Okay, let's change the sphere to a cylinder. Okay, so now we have a cylinder like this. Okay, now we have a cylinder like this. Let the radius of the cylinder be r, let the height be h, let it be a black body. Okay, let it be a black body. Now guys, if I ask you that what will be the shape of a shadow that will be formed on a screen behind this cylinder, can you tell me the shape? Those of you who are able to figure out the shape without going forward in the video, without checking out the answer, please write it in the comment. I will know that how many of you can actually think. The shape of the shadow would be a rectangle. Okay, it would be a rectangle. What would be the sides of the rectangle? The sides would be h and diameter, that is 2r. Okay, and how can I imagine the triangle? So imagine if I split this into two halves, what is the area that I'm going to expose? If I split this cylinder into two halves, this is the rectangle that is going to get exposed, and it is this rectangle which would be responsible for blocking the light. Like, all right, so coming back to the value of force, how much force is acting? Okay, how much force is acting? The force is intensity multiplied by area, so 2RH by C. This much force is acting on the cylinder. Okay, let's see more example. Okay, let's see one more example. Okay, what if we have a cone? Okay, what if we have a cone of radius r, height h, and it's a black body? Okay, think about the shape of the shadow. Students, think about what kind of shadow this cone will make on a screen behind it. If you are thinking a triangle, then you are right. The sides of the triangle, the height would be h, the base would be 2r. All right, if I split this cone from between, this is the kind of triangle that will be exposed. Okay, so the force would be how much? It would be I into half into 2r into h. I've written the area of the triangle divided by c. Remember that it is important the object to be a black body. If it is not a black body, this result is not valid. Okay, so this is the force going to be. So are we clear on what I'm trying to suggest? Okay, let me come back to, okay, let me give you one more example just to ensure that I have driven the point home. Okay, so if this is the radiation, okay, and let's say this is the cylinder. Okay, radius r, height h, and it's a black body. Can you tell me the direction of force, everyone? Can you tell me the direction and the magnitude of the force? Well, now the force, the axis is parallel to the direction of the incident rays. It would be I pi r square by c, because if you notice that in this case the shape of the shadow would be a circle, and this would be the region that would be responsible for blocking the light. So the force would be this. All right, now checkpoint. Let me test whether you understood the concept or not. So you try to answer this question, everyone. Okay, so this is the checkpoint. Let me check the point you have understood or not. So this is the cone. Okay, the same cone situation I'm giving you. This is the cone, and light is coming. A parallel beam, okay, of intensity I is coming. Okay. Now my plan is to cut the cone from different places. I intend to make some cuts on the cone. I intend to remove some part of the cone. Imagine it a solid cone. I intend to remove some parts of the solid cone. You have to tell me that which cut will result in a change in the value of force. Which force? This force. I'm going to make several cuts on the cone. You have to tell me that which cut will change this value and which cut will not change the value. The force will remain unaffected if I make that cut. Okay, so let's see. This is cut 1, cut 2, cut 3. So out of these 3, okay, cut 1 will not change the force. Okay, I'll tell you the reason in a short while. 2 will not change the force. Okay, and 3 will change the force. Okay, so what is that you need to pay attention to? Check whether these cuts are intersecting with this triangle or not. So if you make any cut such that this triangle remains unaffected, it will still block the same amount of light as it was blocking earlier. So 1 and 2 will remain, will not affect the value of force, but 3 will definitely affect the value of force. So I hope we are very clear with this. Okay, now if you have been with me till now, you have done a very good job, guys, because these things generally students don't know. I've seen that students not aware of these things. Okay, now a very special result, a very special result rather. I absolutely love this result because students who don't know this result generally can't solve the question when it comes on this particular topic. So what is that result? Okay, a very special result. Okay, VVS result. Okay, if this is not a perfect black body, this force will change. Is that the result? No. Keep listening. If this is not a perfect black body, this force will change. If this is not a perfect black body, this force will change. If this sphere is not a perfect black body, this force will not change. Okay, for the particular case of sphere, even if this sphere is not a black body, the force still remains the same. Is there any logic that I can give? No, there's no logic. We discover this when we do the math. We need to resort to integration. We need to do certain things. When we do that, this is what we discover. Okay, so again, I'm pretty sure that there are students who want to keep the math out of physics right now, which is a good strategy because the exams are near. You want to know more and more rather than knowing the why and why. All right, so know what and what. So you need to know what rather than why at this point in time because the exams are near. So to know this, I can derive that also. We'll see, I'll see whether I want to do that right now or not. But for the special case of sphere, this remains same. So what if I say that the reflection coefficient is 0.5? The force will still remain the same. Okay, in this case, if I say that the reflection coefficient is something else, let's say 0.5, then what amount of force will act? There is no modification that I can do on this formula. I will have to start everything from the first principles. I'll have to integrate. I'll have to assume vertical strips on the left half of the cylinder. The left half is where the light is striking. So I have to consider that left half as a collection of strips. Every strip will act as a small plane area. Every plane area will have two components of force, parallel and perpendicular. We'll write them, we'll integrate. So a long solution is going to be there and then we will arrive at a result. So it's not that I can simply make some modification to this formula and I can write the force. That is not the case. So these situations, this or this or this will still remain same because that surface is a flat one. What I'm trying to say, if these objects are not given to be a perfect black body, then this question is tremendously difficult. But if a sphere is not given to be a perfect black body and still we have been asked the value of force, it remains the same. So remember this. Okay, and one very important point, I'm saying that R can be anything, but it still needs to be uniform on the side where the light is striking. You can't say that, okay sir, we will have a certain value of R in this region and a different value of R in this region. I'm not saying we are allowed to do that. It has to be uniform. All right, it may have any value, but that value needs to be uniform throughout. Okay, now what was the result? Let's come to this. What was the very special result? So for the case of sphere, even if it is any general value, even if the R is any general value, okay, and this is a sphere, okay, the force is still I pi r square by c. And therefore, if a question comes on the sphere, the question may not tell you whether it's a perfect reflector, it's a perfect absorber, or it's a general case, because it doesn't matter in the case of a sphere. All right, so I believe we have covered a lot of theory now. Okay, let me do some examples with you on the theory that we have covered now. Okay, so let's start with a simple example. Okay, so the situation is somewhat like this, this is a plank. Okay, the thickness is quite small. I'm just showing it to indicate that it's a plank. Okay, a thin plank, you can say, a very thin plank. It is kept on a smooth surface and it is tied to a wall with a string. It is tied to a wall with a string. I want to know the tension in the string. Of course, sir, why will there be any tension in the string? Right now it will not be there, but then I will create conditions that will result in a tension. So guys, now I say that, okay, radiations were incident on this in the form of a parallel beam at an angle theta. The intensity was I. And there's one more thing that I forgot to point out, guys. The expression of force that we wrote, they did not have lambda in them. Let's go back and check. The expression of force did not have lambda in them. Where was that? Here. These expressions are devoid of lambda. They only depend on the total intensity of the beam, which means that when we started with the derivation, we assumed the beam to be monochromatic, but actually it need not be a monochromatic beam. All right, it can be a polychromatic beam also. So yeah, let's come back to our example now. Here it was. So my question was, how much tension will be there in the string? All right, let the mass be n. Okay, and the question can also ask you the normal force exerted by the ground. So what we have been asked is, what is the value of normal force exerted by the ground? What is the value of tension in the thread? Okay, how do we do this? This is at rest. How do we do this? So it's actually, we use Newton's laws. We have been asked the value of force. Most likely we are expected to draw the free body diagram. Let's do that. So this is the plank, and if I think about the forces acting on it, okay, there would be a tension force. Okay, there would be a normal force. There would be an mg force, and apart from these two, there's going to be F parallel due to radiation, and there's going to be a F perpendicular due to radiation. And if you now see in horizontal direction, there are only two forces, so I can write the value of tension as F parallel. So it will become IA cos theta sine theta 1 minus r by c. What about the normal? So in the vertical direction, I see three forces, mg, F perpendicular, and normal. So normal is upward, the other two are downward. So normal would be balancing the sum of those two. So normal would be equal to F perpendicular plus mg. So it will become IA cos square theta and then 1 plus r by c plus mg. Okay, so simple example, I would say, a very simple example. Okay, if you have understood this, let's increase the complexity of the question. So in the same question, or in this, in a very similar situation, now here is a surface. Let the friction coefficient be mu, which is quite small, but it is there. When I say quite small, I intend to tell you that I'm assuming if there is a possibility of motion, it will take place. It is that small. Okay, so we have now a cube. Okay, so this is a cube of side length A. Okay, this is a cube of side length A. Okay, and it is kept in a region where let's say sun rays are coming. Sun rays are coming at an angle theta right now. Okay, although the sun ray may not have enough intensity, but it is coming at an angle theta right now. And let the mass be m. Okay, the mass is m. So this is the situation, and because of the force exerted by the radiation, okay, this object is moving. I want to know its acceleration. Okay, I want to know its acceleration. How do we do this question, guys? Now in this question, how is it different from the previous one? Like we can very well say that in this question, instead of balancing the force, why don't you just simply use net force equals to F m to n? But there is a fundamental difference in this question, guys. In this previous question, I told you that consider this thickness to be negligible. So any ray that could have been incident on this thickness, we ignored that. We ignored that because that area was very small. But here, this area is comparable to this area. In fact, if you think carefully, for this tube, there will be two faces which will receive energy. There are going to be two faces which are going to receive energy, and those two faces are like this one and this one. So these two faces are going to receive energy. So we have to be very careful. Let me do it on the next page. So if I draw the FBD, okay, if I draw the FBD, let me first draw the radiation forces. Okay, so these are the two surfaces that will receive the radiation. Let me call this as 1. Let me call this as 2. So on this surface, there would be an parallel component. So let me write it as F parallel 2. All right. There would be a perpendicular component. So this is F perpendicular 2. On this surface, the perpendicular component would be like this. So this would be F perpendicular 1, and there would be a parallel component F parallel 1. Notice, so these are the radiation forces. Apart from these forces, there is going to be an mg, there is going to be a normal, and there is going to be a friction, which is going to be kinetic, because I'm saying that motion is taking place. Now you have to frame the equation. So and there is another very important thing where the students commit mistake in this question. You can take the angle of incidence as theta here, but understand that here the angle of incidence is 90 minus theta. So you have to be careful on this, that the two surfaces will have different angle of incidences, which means that when you are trying to write F parallel for second surface, you know, it's all good. It would be IA cos theta sine theta and then 1 minus r by c. Similarly, F parallel for the second surface would be IA cos square theta 1 plus r by c. But when you write F parallel for the first surface, now you need to be careful. It will be IA cos of 90 minus theta, which will become sine theta, then sine of 90 minus theta, which will become cos theta, and therefore it appears like there has been no change. And yes, of course, here it has been no change. What is capital A here? Capital A would be A square, okay, because the side length of the cube was A. But when you write F perpendicular 1, notice it will become IA sine square theta into 1 plus r by c. I think the rest of the question you can finish. You know, rest is NLM, Newton's law. You know the forces. You can write the value of normal. You can substitute it here. Net force in the horizontal direction equal to mass into acceleration. That part you all can finish. I wanted to highlight this, that there will be questions in which the radiation will be incident on two surfaces. Those two surfaces may not be parallel to each other, which will make the angle of incidence differ. So you have to keep that into account, that the angle of incidence can change while you are writing the forces. So be vigilant about that. Okay, so that was another question that we could have done. Okay, and now let me again, this next example that I'm covering, it is specifically for JEE advanced student. Okay, which basically means that you can expect this example to be a bit more complicated. Okay, so this is only for JEE advanced student. So situation is this. This is a parallel beam. Okay, this is a parallel beam, and we have kept a cylinder. So this is the same situation that I was mentioning a few moments earlier, that it makes the question very, very complicated. R is not 0. You know, let's say we have R equal to 0.5. I'm just giving you a value so that we can't use the direct rule of black body. We will not be able to use that. The radius and the cylinder is given, like the height is given. This is R. Okay, this is H. We need to find out the value of force acting on the cylinder. Okay, so find force on cylinder due to radiation, of course. How do I do this question? Now, before you start solving this question, there are a few observations that you need to make, or if you are able to observe those things, only then you can you know, hope to proceed in the right direction of the solution. So what are those observations? So first of all, understand that only the left half of this cylinder will receive light, the right half will not receive. So this is the region where the light will be incident, and therefore even if you remove the remaining portion of the cylinder, it's all fine, you will still have the same value of the force. So this is the region where the light will be incident. So this is the first observation that you need to make. The second important observation is that imagine about the angle of incidence on the left portion of the cylinder. Specifically, what I'm trying to ask is the angle of incidence same at all points of the left half of the cylinder? Think about this. Is the angle of incidence same? And if you're not able to think about this, let me give you a different view. Imagine yourself viewing the situation from here. So when you view the situation from here, you will only see this part of the cylinder. Let me make that view. Okay. So the new view that I'm asking you to imagine, the light is coming from this direction. You will continue to view that light, and the cylinder will now appear like this. Okay. So the cylinder will now appear like this. This is the left half. So this is what you will witness. Okay, let me go back to the previous figure. If you are looking from top, you will only see this part, all right, or this face. This part is immaterial, so I'm not paying attention to that. So this is what you see. Okay, and now think of it, whether the angle of incidence is same throughout or not. For example, if I extend this light ray, if I extend this one, if I extend this one, if I draw one here also, do you think that the angle of incidences at these points are same? For example, to talk about the angle of incidence at this point, I will draw a normal. Okay, normal. So do you think these angles are same? I certainly don't believe that. All right, the angle of incidence is changing. All right, so we have to take that into account. Now, if the angle of incidence is changing, I would prefer to choose an element where I can say that for this element, for my element at least, the angle of incidence remains the same. So what kind of element would it be? Okay, so if you notice here, can I say that the angle, the element that I need to choose should be vertical strips, like the left half of the cylinder can be assumed to be made up of these vertical strips, which are arranged in a semicircle. Okay, so if I am able to work out with one strip, I'm good. Okay, so to do that, in this figure only, first let's connect the edges of this strip with the center. So this will be some angle, and now I get some idea what I need to do. So let me do it on a fresh slide. So this is the light energy which is coming. Okay, and then I'm drawing only the left half because that is what is relevant. That will save me space for writing. This is the left half. Now, okay, here in the figure I have drawn I've shown the strip to be in this region, okay, we can continue doing that. So at an angle theta, assume a strip, okay, that will make angle d theta here. Okay, so what will be the area of this strip? What will be the area? It would be h r d theta. Imagine this length would be r d theta. The depth in this figure, I will call it the depth, although in this figure it is clear that this is what has become the depth in this figure. Okay, so depth is h into r d theta, that is the area. Now the ray which is incident here, okay, it is incident like this. The normal would be like this. So if this angle is theta, the angle of incidence is also theta. All right, and we can consider this strip as a plane area. Okay, so there would be a tangential force. So this is tangential force, this is df parallel. There would be a normal force df perpendicular, okay, on this strip. How do I write these forces? So df parallel would be written as I into dA, and then sine of angle of incidence, cos of angle of incidence, 1 minus r by c. Okay, how we will write df perpendicular? Okay, so that would be I dA cos square theta into 1 plus r by c. Okay, I have written these two. What next? Next is that you have to see, if you change the element, the direction of df perpendicular will be different. For example, for this element, the direction of df perpendicular would be this. All right, so if you on changing the element, if the direction of a vector is changing, then you can't simply integrate the vector. You have to take the components of the vector and then you have to integrate. So my plan is to actually define, let's say, this as the x direction, to define this as the y direction, and then I will write dfx. Okay, now what is dfx? This is x component of force on strip. This is x component of force on strip. Okay, so how to write this x component? So notice this angle is theta. So df perpendicular cos theta. Okay, and then this angle will be 90 minus theta. So df parallel cos of 90 minus theta, that will become sin theta. Okay, similarly you will also write dfy. Let's write that. So dfy would be df perpendicular sin theta. Okay, and the other component would be y minus. See, this df parallel is having a downward component, and how much will that be? This angle will be theta. So df per parallel cos theta. Okay, now we will integrate this to get the x component of force on cylinder. We will integrate this to get the y component of force on the cylinder. The integration will be from, if you notice, it will be from minus pi by 2 to plus pi by 2. Okay, it will be from minus pi by 2 to plus pi by 2, and that will cover the entire portion. One of these two integrals will give you 0 answer. Can you tell me which one? All right, the fy one, like fy will come out to be 0. How can I say that? Well, you can finish the math and you can check it for yourself. I'm saying that because in this situation it is pretty evident that the force, we know that in this situation the force will be in this direction. All right, although the magnitude of the force will not be written, like the symmetry of the situation suggests that the force has to be in the x direction. So I know that this I'm going to get 0. F parallel fy I'm going to get 0. Fx, whatever I get, that is the answer. So I'm leaving it here, but you know, the mathematics is lengthy, but it is doable. It's not like it's not something that you will not be able to do. You can certainly do that. Okay, and it is doable. So I'm leaving it here. You will get an answer in terms of r, the reflection coefficient, which will actually confirm the result that I said, that if the cylinder, the cone, if they are not black bodies, then you know we need to find out the answer by doing the math. We can't simply, you know, modify that result to get the answer. All right, guys, on that note, I think we are done with our first part of the of this topic. We said that there are two major situations that are covered in radiation pressure. The first one was parallel beam, like how do you deal when a parallel beam is given to you. So that part we have covered. Now we will start with the second part, which is how do you deal when a point source is given to you. All right, so we'll do that now. So we'll start with the point source now. So this is our second situation now, in which we will be given a point source. Okay, now one very important point of difference from the parallel beam case is that in the case of parallel beam, you are given the intensity of the beam. In this case, you will be given the power of the source. Okay, so if this is a source, its power will be given to you. All right, so it is radiating energy in all direction. Okay, it is giving out energy in all direction. Okay, and power is given to us, and then we would be asked to find out various kinds of things. Okay, we'll look into that. This particular case is very important in photoelectric effect topic also. Like there would be a situation in photoelectric effect experiments when a point source would be used to irradiate light on a metal plate, and electrons will come out of it, and then they will talk about, you know, taking the point source at a distance thrice the initial distance, and then they will talk about the number of photons emitted from the plate, how is that, the number of electrons emitted from the plate, how is that affected. So therefore this becomes important because it is used as one of the cases in study of photoelectric effect also. So keeping attention. So guys, here what is happening, the power given out by the source, it is expanding in the form of a sphere. You are well aware of the concept of wavefronts by now. So the spherical wavefronts are there, and therefore, you know, because whatever power is given out, it is expanding in the shape of a sphere. So at a region R, this power P is crossing a sphere of area 4 pi r square, and therefore the intensity at a distance r will be given as P by 4 pi r square. So this is one of the fundamental things that you need to keep in mind, that how much intensity is there at a distance r from a point source. It is P divided by 4 pi r square. Why this? P power is expanding through a sphere of area 4 pi r square. So power divided by area, that gives the intensity. Now, that is one thing. Now, the situation is this. We have a point source, and at a distance r from the point source, let's say we have a disk. Okay, a disk we have kept, and we want to know how much power will be incident on this disk. Okay, this is what we want to know. So before we start solving this, I want you to imagine, or I want you to consider this. Is the angle of incidence going to be same at all point on the disk? What do you think? Is the angle of incidence, because if you ask me, the radiation coming here will strike at a zero angle of incidence, but the ray which will strike here, it is certainly not striking at zero angle of incidence. Here the angle of incidence is, you know, this angle, you know, at the periphery. If this angle is theta, then it is theta at the periphery, and in between these points it is between 0 and theta. So different points have different angle of incidences, so keep that in mind. Okay, I want to know how much power will be incident here. Now guys, one way is to derive, you know, by assuming concentric ring and checking out that how much power is there on each ring, integrating. That is one of the way. The other way is to actually make use of the solid angle. For example, we know that if energy is given out or anything is distributed in a spherical region, then it is uniformly distributed in a 4 pi solid angle region, 4 pi steradian. Okay, so whatever this solid angle is, okay, I will say that the power incident on the disk can be written as total power divided by 4 pi multiplied by omega. Okay, so that the omega is the solid angle. And how do we write it? So it is 4p by 4 pi into 2 pi 1 minus cos theta. So this power will be p by 2 and then 1 minus cos theta. Now, those of you who are thinking that I don't know what sir did, I don't know the concept of solid angle. So guys, if you don't know the concept of solid angle, ignore it. Okay, don't sweat over it. Just remember this formula, that this is the power that will be incident on the disk. So I'm writing it here again. The power incident on the disk will be written as p by 2 1 minus cos theta, and cos theta can also be written in terms of the radius of the disk and the distance of center of the disk from the point source. How? Cos theta will be base upon hypotenuse. This distance would be root of r square from r square, which we can very easily calculate using the Pythagoras theorem. So it will be p by 2 1 minus small r divided by root of r square plus r square. So okay, so this is the power. Now, for example, suppose if you are asked to find out how many photons are incident on the disk. Okay, so power incident divided by energy of one photon will give you number of photons incident on the disk per second. So this is how you can use it. Now, there is another very important point to notice. Okay, and that is this. Okay, let's consider a special case. In which small r is much greater than a capital R. If I have to describe it in English, in language, I will say that a coin, you know, something like a coin kept, you know, at considerable distance. A coin kept at considerable distance from a point source. That is the situation. Okay, a coin kept at a considerable distance from a point source. So that is the situation. So in the figure, it would look somewhat like this. Okay, this is how it would look like. Now, in expression, what it would become, let's see. So power intercepted by the disk is the coin here. It would be p by 2, then 1 minus r divided by, let me write the expression first, and then I will do some calculations. So it can be written as P by 2 1 minus R divided by R can be taken out as a common quantity. So it will become 1 plus capital R square by small r square raised to power half. Okay, this R gets cancelled. Okay, and now we can use binomial theorem. So P by 2 1 minus and then 1 plus R square by R square raised to power minus half. Okay, and because capital R square by small r square is very small as compared to 1, so we can use binomial theorem. So it will become P by 2 into 1 minus 1 and then plus R square by 2R square. It will become 1 and 1 gets cancelled. So it becomes PR square by 4R square. Okay, and then if you multiply with pi in numerator and denominator, what does it become? It becomes P into pi r square, that is P into area of coin, okay, divided by 4 pi r square, or in other words, power incident on coin, this is intensity into area. Okay, P by 4 pi r square is what? This is intensity at the location of the coin into the area. Why did it become like this? Like any reason? If you check this, if I try to draw the rays that will be incident on the coin, okay, scale would have been better. I'm trying to do the freehand drawing. And if you try to draw all the other rays that will be incident on this coin, okay, and then if you choose to ignore this part of the figure, I'm trying to hide it using my body. So the rays hitting the coin, does it look like a parallel beam? By the time they reach the coins, they start appearing in the form of a parallel beam. And how do we write the power incident in case of a parallel beam? We write incident intensity into area. So that's what we are getting here. All right, so in this case, it's very simple. You can just notice the intensity at the location of the coin and you can multiply with the area of the coin. If the coin is tilted at some angle, then you would have a cos theta factor also, where theta would be the angle of incidence. Okay, so guys, this situation is used a lot in framing questions, especially in photo electric effect. For practice sake, let's do an example. Think about this. A point source is kept here, power is P, and then there is a sphere here. I want to know that how much power will be incident on the sphere. Okay, so this distance is R, this radius is capital R. I want to know how much power would be incident on this sphere. If you are writing the same expression as we wrote for disk, then you are wrong. What you have to notice here is this. You can pause the video, you can give it a thought, and then you can continue. If I draw tangents on this sphere, okay, then this is the region which will receive light. So either you can calculate the radius of this disk using geometry, you can do that, or you can directly talk about this solid angle. If this angle is theta, okay, you will write power received by sphere, you will write it as P by 2 into 1 minus cos theta. And now notice how theta would be written. It would be 1 minus, this time notice that this angle is 90 degrees, so R becomes the hypotenuse, and this is what? This is R square minus R square. This becomes base. So root of R square minus R square by R. Okay, so this will be the power received by the sphere. So I hope you understand this part, everyone. So now you can practice it. Okay, and let me also give you a special result, okay, without derivation. Okay, it may be useful in some situation. If we have a hemispherical bowl, okay, and if we keep a power source at the center of the bowl, okay, you can expect that the radiations will go and get reflected like this, depending upon whatever is the value of reflection coefficient. Some part of the radiation will be reflected back. Okay, so if I ask you now that in which direction do you expect the force to be on this hemispherical bowl, you will probably say this because of symmetry, which is correct also, and this force will be given as P into 1 plus R, okay, by 4C. So this is the formula. This is derived on the basis of integration. You can just remember it and you can use it if there is a need. All right, guys. So that brings me to the conclusion of this session, where we talked about radiation pressure. if you watch this session carefully, if you have done everything that I did in this session on by your own hands, by writing in your rough copy, by doing everything with me, then there are good chances that you will be able to solve any other question on radiation pressure that is given to you. You need to know other formulas like the energy of a photon, like how do we write the energy of a photon. All right, it's 1242 by lambda, where lambda is in nanometer, and the energy that you get is it's an electron volt. So there are other formulas that you are need to be aware of. I'm expecting that you are already aware of those formula. It is this part that I covered in today's session that I've seen that the students don't know. All right, so this should actually bridge the gap that is there that makes this topic difficult for you. So I hope it will help you. I'll bring more such sessions, guys. Keep looking out in this particular channel, and I'll see you on some other day with some other session. Take care, students. Bye bye.